Hello and welcome everyone to our inaugural webinar called Panelize the YAS Marina Hotel with EvoluteTools for Rhino. We are very happy to have so many of you here and thank you very much for your interest in EvoluteTools. My name is Matthias Höbinger. I work for Evolute as a consultant and software developer, and my educational background is mathematics. The title of today's event is inspired by the first large project that our company worked on a few years back, the YAS Marina Island Hotel in Abu Dhabi. Evolute itself was founded in 2008 as a spin-off of a university research group in Vienna, mainly with the goal to provide specialist geometry consulting to everyone concerned with designing and building complex architectural structures. 2010, we decided to make parts of our quite powerful software library publicly available as a Rhino plugin, and eventually this became EvoluteTools for Rhino. The software is mainly a tool to create and then optimize panel layouts for various types of freeform surfaces. We've been using the technology in the plugin for years in our real-world projects, among them the YAS Hotel itself. And since its introduction as a software product, it is being used by a number of renowned offices in the industry. But I don't want to say too much about the plugin itself here, because seeing Florian use the software is, of course, much more effective than me losing too many words about it. I want to share some quick news with you. Number one is that we are excited to be giving a workshop at the Design Modeling Symposium in Berlin in 10 days, where participants can get a day of hands-on experience with EvoluteTools. There are still free spots on the workshop, so if you have the opportunity, we'd be very happy to see you there. And there's also an important announcement for the students amongst our audience. You will be able to buy an educational license for EvoluteTools for 250 euros at this workshop in Berlin. Then the second news that I want to share with you is our blog. We just started a blog a couple of weeks ago, where you can always find up-to-date information about what's going on around Evolute and EvoluteTools. So, for example, right now, obviously the announcement of this webinar. And the second thing that we're really excited about is the availability of the T-Splines bundle. Recently, we have been working closely with the T-Splines team. Here you see our web shop with the availability of the T-Splines bundle. We've been working with the T-Splines team to see how our products can work together, and we're really excited about the capabilities of the combination. So we thank the guys at T-Splines very much for all their support, and we'll continue to work on delivering a really good, powerful modeling and paneling package together with T-Splines. Back here. So here it is. That's the YAS Marina Island Hotel on the Formula One track in Abu Dhabi. As you can see, the geometry of this glass and steel structure is quite complex, and we are very proud of having been able to contribute to it. The client that Evolute worked for in this project was Wagner Biro Stahlbau, a specialist contractor who built the whole structure in Abu Dhabi. And what we delivered to them was an optimization of the panel layout, as I've said, using the same technology that's now included in EvoluteTools for Rhino. Now, as I've said, we like the project very much, and also the way it has turned out. And because this geometry and topology of the form is very nice and quite complex, we thought its reference surface would provide a great challenge to demonstrate the features and capabilities of EvoluteTools for Rhino. So this is exactly what we're going to do in this webinar. And so with that, I'd like to ask Florian to take over and start his presentation.
Hello everyone, welcome to our debut webinar. I would like to apologize if the hour of the webinar was not very suited for some. Hopefully you didn't have to stay too late to watch it, and I hope this is going to be worth it. I'm Florin Isforanu. I'm an architect by training. I got my degree in Bucharest, Romania, and I joined the Evolute team this year in May. So today we will start to use our plugin, EvoluteTools for Rhino, and show its capabilities using the YAS Marina Hotel as a reference surface. In order to better explain or have a proper pace for everybody in the webinar explaining things, I would like to set up a short poll just to see how many of you are familiar with our tools. And Matthias, if you can fire up the poll, that would be great. Okay, we have a pretty good mix there. So I will start to explain the basic functionality of the plugin. So as Matthias said, this enables easy paneling layouts on freeform surfaces, and of course the optimization of these panel layouts. So the functionality involves taking an input surface, which can be a NURB surface or a T-spline surface, or just a simple mesh. And the next step is to build a coarse mesh that just roughly resembles the shape of the input surface. Then use some subdivision tools on this coarse mesh, and by optimization, the plugin will just force this subdivided mesh to take the shape of the input surface. Now let's meet the YAS reference surface. And as you can see, the geometry is pretty complex. It's got these openings on top, and the geometry changes curvature from concave to convex. So this is a pretty tough challenge to panelize and optimize. So without any further delay, I will just start to work on it. I'll just go to shade mode just to see this thing a bit better, the meshes. This is, as I said, this is just a mesh for now. We have a pretty dense mesh of the YAS gridshell shape. And I will start with a really coarse mesh, as you have seen in the previous slide. And I will subdivide this coarse mesh and then force it to take the shape of the input surface. So first I will just make a copy, a rough copy, and put it over the reference surface. I'll hide this one for now. Because the reference surface is a really dense mesh, I will want to hide it most of the time just so you can see better the results of the optimization. And first, I'm going to duplicate the borders of the reference surface, and I will group them and just keep them visible, but I'll just hide the reference surface just so we can see better what's happening, because this is pretty dense and it just clutters up the display. So I will hide the reference, and right now I can start the subdivision. Just a few words about the coarse mesh. As I said, it just has to resemble the shape of the input surface roughly. And as you can see, this is pretty coarse and almost brutal in some aspects. So it doesn't have to be really detailed from the beginning. You can just start with a really simple coarse mesh and optimize it, and then refine the results if the panel layout is not yet up to your expectations. So I will start with a simple Catmull-Clark subdivision. Sorry, I did a diagonalize. So Catmull-Clark, let's do a couple. And I will just delete the coarse parent. By using subdivision like Catmull-Clark, you can see that this algorithm will try to smoothen the mesh, so we don't have those jagged corners anymore. And I already have the YAS reference surface set as a reference, and I can start the.
Sorry, Corinne, could you maybe try turning the thing around a little less so people can follow what you're doing?
Okay. Yeah. Thanks. All right. So I'll just put all the optimization importance to defaults first, and let's have a look at the options. So we have surface closeness, curve closeness, original closeness, normal closeness, and a lot of other parameters here. And for starts, I will put a bit of fairness curvature, say 0.3, and a bit of fairness springs, just to keep this mesh tight so we don't have vertices going off too far out. So this is ready. I can start the optimization. Just hit the optimize button, and you can see the vertices are moving around a bit. And let's have a look at the borders. And this is pretty close. The vertices here at the border are almost on the boundaries of the reference surface. All right, so let's get some other optimization in. I'll try to orbit around it, less. First, I will want to set a row of vertices to become normal to the base plane, so we don't have a lot of movement or warping of this, basically this spine of our panel layout. So I will select a set of vertices. Let's get these ones, Let's get this one too, and a set of vertices from the back there too. I'm finished selecting, so I will set them to become coplanar first, and I will put them not a general plane, but I will use a parallel plane to the ZOX plane. So let's find this ZOX. This is good. And the reason for this is that I just want them to be, for one, normal to the base plane, but also parallel to that ZOX plane. So this is a quick way to do it. So this is set, and in order to optimize for coplanarity, we have to ramp up the coplanarity parameter. So here is coplanarity. Let's go to 1. Optimize and see what happens. Just hit the optimization button. And we have these sets of vertices now nicely aligned. Let's check that alignment first. So I will go to ET-set vertices coplanar, and it just shows us the set of vertices that are selected to become coplanar, and we can show the plane where they sit. So let's orbit just a bit around it. We can also check the distances for each vertex to that plane by just clicking this show distances from plane, but we'll not do this right now. Alright, so this is nicely aligned in a plane. We can delete the plane for now. I'm happy with it. So let's look at other ways of optimizing this mesh. Another thing you notice here, there's a lot of movement in this vertical, almost vertical polylines. So I will actually want to set a couple of them to become normal to the base plane too. So I'll just select them. Let's say this one and this one. Hopefully they are aligned in front view. Let's check the front view. Yeah, they're almost overlapping. Let's go to perspective again and just set them to become coplanar. So for now we'll have to use a parallel plane to the YOZ plane. Let's find YOZ. Here it is. And optimize. Let's go to front view so we can better see the result. So I think these sets of vertices are set to become coplanar. Let's see how it looks. Oh, we have to select the mesh, of course. And the result is, of course, pretty instant. I'm happy with it. Let's have a look at some other rows of vertices and what can happen there. We have here this transition shape between the large openings, and there's a bit of movement there. And I can also optimize some of these sets of vertices to become coplanar in a plane normal to the base plane. So I'll just have to select a set. Let's pick this one, set it to become coplanar, and I will use the same YOZ plane. Yes. Hit the optimize button, select the mesh, and it's done. At any point, if we have many sets of vertices that are set to become coplanar, we can simply check them out by clicking the button, selecting the mesh, and we can browse through them by using previous and next. And you can, of course, remove them if you're not happy with them anymore. All right, let's get some other optimization done. You can see here at the edge of this opening, we have a bit of bulging up of the polylines, of the mesh layout, and I really want to get rid of that. I'll have a look at the optimization parameters, and I think it's because of the fairness spring, so I'll put this to 0 and optimize again and see what happens. Yeah, got rid of those. One thing you will notice with EvoluteTools is that when you start to work with it, you will see that all these parameters, it's pretty easy to foresee what they will do, and once you work with it, you will know pretty much just the right amount of importance you have to give to each parameter in order to get the desired result. So it's actually pretty easy to foresee what they will do. For example, the furnace springs will basically simulate the presence of a spring between the vertices of this mesh. So this is pretty useful when the mesh starts to bulge up in some area and you need to basically tension it so you spread it nicely over your reference surface. Okay, let's check the mesh further and see what we can do with it. Let's go to front view, and I want to have a look at this area here. And of course we have some movement, and in order to keep these seams better aligned or in line or contained so they don't move a lot around your reference surface or basically slide on top of your reference surface too much, you just set a few constraints like the coplanarity. So I will select a few more sets of vertices, this one and this one, and I'll set them to become coplanar again. And I think this is, yes, this is the YOZ plane. All right, so this is done. Let's optimize again. Select the mesh, and they're not perfectly aligned in a plane. Okay, perspective view. Good. Let's have a look at the density of these panels. So the size of these panels, it's like 8 meters now by 2.6. So this is a bit unrealistic for building this like 1-to-1 scale. So we'll have to subdivide further a bit. Okay, so this is pretty nicely aligned and fair, this mesh layout right now. So I'll do a Catmull-Clark again on it, so we get a bit more density. I'll just delete the parents, I don't need it anymore. Let's have a look at the panel size. So we have 4 meters by 1.3 meters. So this is still a lot. I mean, the panels are pretty big. When we started working on the YAS Marina project, we had different constraints like the fairness of the seams of the panel layout. Of course, we don't have a diagrid at this point, but we will have it a bit later. So until that moment, we'll just play with this simple quad mesh a bit more. And another way of optimizing this quad mesh is to optimize the planarity of these quads. We have a bit of gap here between the borders, so this is simply due to the subdivision, the Catmull-Clark subdivision I just did. I'll just hit the optimization button one time, and yeah, that's sorted. Let's have a look at the planarity, so the analysis modes. So let's set the range, and let's have a look at these numbers here. So we have 15.15 meters. We have a drop-down menu here. We can select centimeters. All right, so we have 15 centimeters, and this is the diagonal distance of these skewed faces here. And this is a lot. You really can't build this with flat glass. Although it was not the case of the YAS Marina to be built with actually for this mesh layout to have planar quads, because the glass panels of the YAS Marina are basically set up in a way that they have an offset from the gridshell surface. So planarity was not a requirement there, but we will optimize this for planarity just so we can see how this thing can be optimized further. This is one of the analysis modes. This is planarity, and we can also check the closeness to our reference surface. Let's set the range, and we have 12 centimeters, and this will be in the red areas. We don't have a lot of them, and the distance is quite good for such a huge grid shell. This big span, the 12 centimeters, it's quite a good number. Another mode of analysis we have in our plugin is the edge length. So we can have a look at the edge lengths, so you can see the distribution of the edges of these panels, and you can of course optimize the edge lengths so that you will have a more uniform spread of these panels on your reference surface. And hopefully we'll have some time to do that in the webinar. All right, let's get back to planarity. we also have the planarity scale invariant. So this analysis mode basically gives us a number, and this is unitless, it doesn't have a scale, and this is basically the diagonal distance of the most skewed face divided by the mean diagonal length. So this is unitless, and it's basically like a coefficient, and you will know that below a certain number you can cold bend glass to take a certain position. So this is very useful. Let's get back to planarity and see how it can use the planarity optimization to get these chords flat. Alright, so let's have a look at the options. Let's put some planarity in. I'll ramp this up to 2. Just a few words before optimizing the planarity. You have to realize that the flatness of these chords is actually highly dependent on the geometry of your reference surface, because if you have a lot of curvature and a lot of transitions from concave to convex curvature, it's going to be pretty difficult to get everything nicely flat. So this is not about the plugin being powerful or not, it's just geometry laws. So this is something that the plugin can be really be used to get these panels flat, or at least to realize where you have issues, and if you will have to change maybe the pattern of your panel layout in order to better accommodate this really powerful constraint, the planarity. Alright, so I just set the parameters, I ramped up planarity, and let's optimize and have a look at the results. So you can see that the vertices are starting to move quite a bit. Let's check the range again, and now we're down to 4 centimeters as the distance between the diagonals of the most skewed face, and we only have a lot of them, which is quite, it's here and it's here, and this transition from these 2 openings, it's a pretty difficult area. We have a lot of curvature there, and there's the transition from going concave to convex, and this is a pretty tough area. We can go further a bit. Let's just ramp up some of the planarity. Let's go to 4. Another thing you can do is to actually downgrade some other parameter like surface closeness, and surface closeness will simply tell the optimization algorithm to keep your mesh layout, your panel layout really close to your reference. So when you will optimize for something like planarity, if you downgrade the surface closeness, you'll have a bit more freedom to optimize it. So let's go to 0.7 and see what happens. Okay. So we have a bit of movement, of course, in the vertices. The color-coded display is definitely showing the difference. Let's set the range again, and we're down to 1.9 centimeters, and we have just a few panels here with well, they are pretty warped. Another thing we can look at is the planarity scale invariant, and let's set the range, and this is actually a pretty good number. So yeah, even for this really challenging shape, the planarity still works. Of course, there are downsides, no doubt about it. You can see that the power of the optimization algorithm is desperately trying to move these vertices on your reference surface in order to get all those quads flat. So this is basically when you have some bunching up of your panel layout in some areas. This is basically a really good way to tell if your panel layout is really suited to get really flat quads everywhere on your surface. But of course, we do have them on most of the surface here, and yeah, this is what the plugin is for, to improve the results and to lower the costs of construction by optimizing this grid shell, this panel layout. Good, we played with planarity. Of course, we can optimize this further by trying to set a few constraints to relax the mesh in this area a bit, but I want to show you a lot of other stuff, so let's move on. As I'm pretty sure a lot of you know the YAS Marina appearance. It has that diagrid pattern on the shell itself, and we will achieve that in just one subdivision step. Okay, let's close the analysis mode, select our mesh, and subdivide it with diagonalize. I'll just delete the parent, I don't need it anymore, and we got this beautiful diagrid pattern on the panel layout. As you can see from the beginning, just from one step of subdivision, it is pretty smooth and nice, and the quads are nicely distributed on the reference surface. We have a bit of a gap here, of course, this is from the subdivision, and we will just do a couple of optimization steps to get this this diagrid pattern closer to our reference surface. First, let's have a look at the closeness and set the range. We're in centimeters, and we are 10 centimeters away from our reference surface. This is in this area here. So let's optimize this diagrid pattern to better take the shape of the input surface. So I will reset all the optimization options to default again, just to start clean. And I usually only start with the surface closeness, curve closeness, and something like fairness curvature. This is just to keep all these polylines, all these seams nicely in line without a lot of shifts and warps. So let's get this to 0.3 and see how it looks. I will hit the optimization button. Also, the color-coded impression of this this mesh layout really shows when you're optimizing how things change. And I hope the density of the panels is just good enough for you to see it properly on the screen. The mesh has a pretty nice uniform distribution of panels. This is what we are after, actually. And there are no major shifts or kinks in the mesh layout. Yeah, this is nice and uniform. I hope there is enough frame rate for you to see this. I'm actually pretty happy with the result. And as you have seen, we just did a few optimization steps and a few subdivision steps, and we got our result. All right, let's close the analysis mode. So this was one of the coarse meshes we used for starts, and we will use another one just coming right up, and we will compare some of the differences between the approaches of the coarse mesh. There's a small detail we're missing here. I'll just add it. This is some local subdivision. What did I do? Oh, I did the optimize. Okay. I'll just add a diagonal line. So this is a nice way to get some local subdivision. I think this line actually represents one of the structural members of the grid shell. Alright, so this is nice and uniform. I'm pretty happy with it, and we can actually move on to use a different coarse mesh that actually has a different singularity layout. As you can see here, we have a singularity here. We have some variance 5 vertices on the grid shell, and we will try to see if a different connectivity of a different coarse mesh works better. Again, we have a variance 5 here, vertex, and almost mirrored to the other side. So I will just put this optimized mesh aside for a bit. I think I'll just hide it. Yeah. We still have the boundaries of the reference surface in position. I'll just change them to a different layer. And let's open up a different coarse mesh with a different connectivity. I'll just roughly copy it onto the reference surface and just hide this one, so maybe I'll just use it later. Alright, so we can see from start the connectivity of this one is a bit different. I have to remember to orbit slower. You might not have a really good frame rate. I'm just positioning it roughly over the reference surface. And yeah, going a bit low. And yeah, definitely we have a different connectivity here. We have a Valiant 6 vertex here and another one here. And as you can see, the singularities are almost hidden up on this top spine of the structure. And this might actually be way better from an aesthetic point of view because you hide those singularities and they're not in front of you. So sometimes singularities can be a bit of a pain. But this is a nice way to shift them in some other position on the surface where yeah, it's just better aesthetically. Alright, so we will start to subdivide this again. I have my reference surface set. I'll just do a couple of Catmull-Clark subdivisions on this one. I'll delete the parent. Okay. You can check out these singularities again. As you can see, except those areas, we have a nice distribution of panels and really nicely continuous seams throughout. Alright, so let's optimize this. Let's take a look at the optimization parameters. We have surface closeness, curve closeness, and furnace curvature. Everything else is set to 0. I will keep this, and let's just start the optimization. And from the start, we have a lot of movement here. Just don't worry about it. Just optimize further, and things will just pop up into position. And if they don't, as I said, the optimization parameters are pretty predictable, and in this case I will just ramp up the fairness springs just a tiny bit and you will see that it mends everything. Alright, so I set a bit of fairness springs there. This basically simulates springs between the vertices, and as expected it really relaxes this this mesh layout onto your reference surface. Great. We have a good distribution, nice uniform distribution of panels. We can again start with some optimization like putting all this spine, this row of vertices in a plane. So let's select those. I get this one, let's get some other one here. That's this one. All right, ready with the selection, and I'll set them to become coplanar. And let's put them in a parallel plane to the ZOX plane. Let's find it. ZOX, this is it. All right. Another thing we can do, for example, if you set a set of vertices to become coplanar in a plane, you can fix one vertex. So in this way, you make sure that the plane where all those vertices will sit will also go through this fixed vertex. I hope this is one of the vertices I set. Okay. All right. So let's optimize. Also, remember to ramp up coplanarity when you set those sets of vertices to become coplanar. I set it to 1, and let's optimize. All right, this is nicely aligned, and maybe it's not actually on the top of the spine, so we will trick this thing into look better. So let's go to set vertices coplanar, let's select the mesh, and check out the plane where those vertices sit. And right here, this is actually not on top of the spine, and it's a bit shifted to the right. So what I will actually do is simply rotate this plane from this vertex. Let's do rotate. Actually, I picked a midpoint from somewhere. Let's do this again, point. I hope you have enough frame rate to see this, and I'm just rotating this plane a bit to the left. Let's do a bit more. Unfortunately, this doesn't mean that automatically those sets of vertices will become coplanar in this one. Select to show the plane. This is basically just a normal Rhino object that basically shows which was the plane where those vertices sit. So what I will do now is set those sets of vertices to become coplanar, but to stay in this actual plane I rotated about. So let's select the mesh, go to set vertices coplanar, and we have this set of vertices. And as you can see, the plane I rotated is just a bit shifted to the right. So we have the plane type here, parallel plane to set OX. So I'll click this and I'll select a fixed plane. And we have the option to select the plane normal, or do a fixed set coordinate horizontal. So I will select this plane. This is set, and I can now optimize, and we will see how these sets of vertices will shift to this position. Okay, now I can delete it. I'm pretty happy with it. We've got that spine nicely set up there. We have a bit of movement here. I will want to set this coplanar to, let's go to front view. And we have a lot of movement here. Actually, I will set this one and this one. Let's set them to become coplanar, and I will use YOZ. Yep, they are selected. It's ready for optimization. That's just like snapping your fingers. All right. So in order to get that diagrid impression again, we'll have to subdivide this. This just slightly optimized mesh. This is now basically optimized for fairness and a bit of coplanarity, just to keep those the major distribution of panels in shape, you know, to align, for example, like with this spine here. So let's do a Catmull-Clark again, or actually this size is quite good. Let's just do the diagonalized subdivision, and this looks pretty good. I'll just delete the parent mesh. Again, we have a really nice distribution of panels. It is nice and fair. And compared to the coarse mesh we worked earlier on, we have these singularities now shifted here up top. And this is actually pretty nice. It's not visually bothering us anymore there. All right, another really cool thing we added in this version of the plugin, and by the way, I'm using the version 1.2 of our plugin, and this will be coming out pretty soon. We're pretty excited with it. We have a lot of new stuff. So what I wanted to show you is some of the features that actually we have some features that can control the fairness locally. So what we have here around this singularity, as you can see, we have a lot of big panels, and we just don't want that. I mean, we are after a nice distribution, nice uniform distribution of panels. So in order to control this this distribution of panels here, we'll actually alter some of the fairness properties. So let's turn the grips on. All right. I'll select these vertices here, and I'll do something really funky with them. Okay, vertices are selected, and we have a new command here, et select vertices fairing, and we can control the local fairing for some sets of vertices, and this can have, well, I don't know, different outcomes. For example, you can tighten up a bunch of vertices, or just control the fairness for a sets of vertices, you know, aligned sets of vertices. And in this case, this will actually tighten up this bunch of vertices, and we'll have a better distribution of panels there. So we can actually set the fairness importance locally there. We have 0.2. You have to use this with caution, because this is actually multiplied with the fairness curvature from your general optimization parameters. So I'll keep this to 0.2 now. Yes, enter. All right, and let's see what it does. Okay, so it tightens this bunch of vertices a bit, and we can actually ramp that up a tiny bit. And we just select the mesh again and run the command etset vertices pairing. And we will just ramp up the importance. Let's go to 0.3. And optimize. Good, it tightens up. Okay, let's have a look at some mesh editing tools. Let's say you want to get rid of this set of panels here and try to see how that singularity looks if you had a variance 5 vertex here. So we just delete a bunch of faces, and this is one of the nice things I really like about the plugin. You have a lot of freedom in manipulating these meshes in order to get the really good result you're after. So I'll just move these vertices to the other side. All right. We don't have a lot of time left. And let's get this one over this one too. All right, so remember that every time you do any kind of operations to a mesh, like deleting faces or adding faces, or just moving some big portions around, filling them up with other triangles and stuff like that, you have to do a welding. So we'll weld this mesh again, and it removed 8 vertices, so this is nicely done now. And let's just optimize and see what the result looks like. So this is actually quite good. We have a better distribution of panels here. We have some nice continuity from side to side. And this is a really nice way to alter your panel layout and improve it. Okay, we can actually do this for these sets of vertices right here too, but we already did it, so this is no longer a priority. There's a detail missing here. Let's get this done. All right, so we can now set this away. I'll just move this aside a bit and hide it, and we'll compare it to the original coarse mesh we worked on earlier. Now, another thing I want to do in this webinar is to just create a coarse mesh from scratch, because this is probably one of the, I don't know, maybe for some it's one of the least exciting stuff when you're working with our plugin. I actually like it a lot, and when you're dealing with freeform surfaces, and then you have to basically wrap them again in some coarse mesh, this sometimes might be hard to grasp, or it might be difficult for you to know where you should start with. But I always try to keep things really simple, and I always, well, or at least most of the times, I just start with a simple quad face. I mean, nothing can be simpler than that. And believe it or not, this is my coarse mesh. Okay, so you will just see in a minute what I can do with it. So I will start with a simple loop cut local subdivision, just because of the aspect ratio of this really big face. And I will do a Catmull-Clark subdivision a few times. I deleted the parent, and again I will edit the mesh, and I will delete a bunch of faces. So I will really want to manipulate this mesh into having a certain appearance I am after. So okay, let's delete a bunch more. Nice and quick. And yep, this is the coarse mesh evolving. So I will turn the grips on, select this bunch of vertices, and select this bunch of vertices, and I'll just move them. I'll just translate them on the Z. Okay, pretty tall, that's good. And what else? This is not very close to our reference surface. I'll turn the grips on again, and I will scale this stuff basically a bit. Let's put it closer to our reference. And from my experience right now, these corners will not work too nicely on our reference surface. So I'll do a bit more editing. I'll just delete these corners, and pretty soon my coarse mesh will be ready. And I just remember I started with a really simple quad face. So this is 5 minutes of work, and you have a really good starting coarse mesh, and it's just enough to see how good of a distribution of panels you can put on your reference surface, and then it's really easy to improve it or modify it. Okay, again, I did some operations with the vertices there, so I will weld this mesh first. All right, and I will do a couple of Catmull-Clark subdivision. That's just fine enough. And yeah, this is coarse mesh evolving. Let's check the optimization parameters: surface closeness, fairness springs, and fairness curvature. Let's leave it like this. Coplanarity, we don't need it. And optimize. Yeah, nicely done. And this was, I don't know, 5 minutes of work. Yeah, we have a situation here. Let's go back a bit. And definitely this is a bit too far from our reference, but I'll fix this in a second. I'll just roughly drag this portion here over the opening there on the top, and I'll optimize again. So I think this should fix things. Yes, so we have a nice spread of panels over our reference surface. And of course we can subdivide further. So this was basically 5 minutes of work. We started with a really simple quad face, and we built a coarse mesh out of it. So this is a really fast way to build coarse meshes. And you can alter the density in some of the areas here. We can delete a few polylines. Oh, sorry, whole polylines, not just edges. All right. And we can optimize again and see how it distributes the panels over the entire surface. This is nicely done. Now, maybe these singularities here are not in the most fortunate places, that's for sure. However, as I said, this is a pretty fast way to build up a coarse mesh and at least get an idea of how the distribution of panels will be on your reference surface. And then you can, of course, improve your coarse mesh. I will do one more Catmull-Clark subdivision to get a bit more density, and then the diagonalized subdivision to get this diagrid look. Just a bit of optimization to make it really close to our reference, and this is pretty much done. There's a tiny detail missing. All right. As you can see, we have a totally different type of distribution of panels here. So the loop, actually the panel line went all around that opening, and we will do the same here. So yeah, we have a pretty different result this time, but still it's quite good. All right, so actually let's compare these results right now. And we are almost running out of time. We'll just have a quick look at these surfaces, at these mesh layouts here, and then we can actually answer some questions. This panel layout is a bit more dense, this is for sure. We actually did a bit more subdivision there. But pretty much the results, the resulting mesh layout is very nice and uniform, and you can be the judge for yourself and start to think of how you can create a coarse mesh in order to nicely cover a pretty complex reference surface and also keep an eye or account for the singularities and where those singularities will be, because this will affect the aesthetics of your project. So here we have the singularities here, and the other meshes there. Okay, Matthias, can we start to do we have some questions?
Actually, I was going to encourage our audience to ask some more questions, because we don't really have very many right now. So maybe you can go on for like a couple of more minutes, and we'll see if there's more questions coming in. Otherwise, you just have a little bit more more time to continue. Okay?
All right, sure. Here we have the singularity here and here. And right here we have it on the top. And if you're looking at this mesh from the sides, it definitely looks, it's a bit cluttered now. but we don't have that singularity there, and the distribution of panels on the sides is way better. And in this example, this really dirty, quick and dirty coarse mesh creation, we have the singularity is actually at the lower boundary. This is definitely not the most fortunate solution, but at least we had a panel layout in something like 5 minutes, and we were able to assess it and see how we can change it or improve it. Yeah, so this is a really good way to use the plugin for, and as you have seen here, the results can be pretty quick. Okay, I see there's a question here. Can we show a hex mesh pattern? There's a quick way to do a hex mesh here. Let's see if we can get this done. It's not going to be pretty uniform, I think. Actually, let's just see. I'll add some parallel diagonal lines with no interval on this mesh and on the lower one. So this basically gives me only triangles, and because I have triangles now, actually it's pretty nice and uniform. It's nice distributed. Let's just delete this or hide this once. Yep. I'll put it over the reference surface again. And let's just do some dual subdivision, dual with boundary, and this will get us some hex meshes. We have dual with boundary here. Yep, I just deleted it, and we had a hex mesh. Yep, I hope this answered the questions. The question actually. I will move this aside, and I will do some other subdivision on it. Hopefully this will be pretty interesting for the audience too. So we have a hex mesh here. The display update is pretty slow. Don't have a lot of frame rate. And I will do a tri-hex subdivision. Okay, so we had a singularity here. And because of the singularities, yeah, it wasn't able to subdivide into a clean tri-hex mesh. Let's see if we can do this to the other ones.
Okay, I mean, we have a few questions now. Maybe I'll
okay.
Call up one or two. Christopher asked if the result is a normal Rhino mesh, because he thought that Rhino can only handle tri and quad meshes. Maybe I'll answer that question directly, because I'm on the developer side here. You are absolutely right. Rhino can only handle triangle and quad meshes. So what we display is not a standard Rhino mesh. We still hope that Rhino will support this display of n-gon meshes, as we call them, in the future. But right now it's a fix. You cannot do everything that you can do with proper Rhino meshes with these higher degree polygon meshes, but we've just added a new option in this new version of the plugin, so you can export them now to a couple of formats that can actually handle these types of faces. I hope that answers your question.
Yeah, we did a tri-hex subdivision here, so we can test it. This is basically a new subdivision rule in 1.2. We have tri-hex here. Yeah, let's just select tri-hex subdivision, and gets us this combination of hexagons and triangles. And we can, of course, optimize this for smoothness and to get a really nice and uniform, nice distribution over a reference surface. Yeah, any other questions?
Yes, there's another question. Is it possible to optimize for a uniform panel size?
Yep, let's see if we can try one of these panel sizes. The panel size optimization, we have two optimization parameters. We have the ideal edge length in the new version, and we have ideal panel. So the ideal panel will try to get the panels close to the aspect ratio of 1. And the ideal edge length, of course, will try to get all the edge lengths almost equal, or equal if possible. But this is highly dependent on the density of the coarse mesh and the distribution of the coarse mesh panels over your reference surface. So let's try to put one here. I will. Okay, yeah, I have to close that. Hide this one. Hide this one. Hide this one. Get this one over here.
Maybe I should add a little disclaimer to the ideal panel option. That is actually under quite heavy development right now still, and I'm not exactly sure if the ideal panel option will make it into the next release. It's not a very simple task because there's very many different types of panels that you could have on such a mesh. But the ideal edge length will definitely make it in there, and we're continuing to work on the panel.
This shape is probably not the best shape to demonstrate the ideal edge length on because of the distribution of panels, and because as we said in some of the tutorials, all these parameters here will basically try to fight each other in order to get to a solution. So I have ramped up ideal edge length a bit. Actually, let's put it a bit more, 0.4, and hit the optimization button and see what happens. We should see a lot of shifts in the seams here, but we will probably lose some of the smoothness. Okay, so yeah, as I said, this is probably not the best reference to show the ideal edge length. Maybe if I ramp it a bit more, let's see one. Yeah, this is basically the optimal solution for this mesh currently. But we tested the ideal edge length optimization, and it works quite nicely. But as I said, it is highly dependent on basically the filling of panels onto your reference surface, because it depends on the aspect ratio of the panels from the coarse mesh and how they are distributed over the reference surface.
Yeah, there's a couple of similar questions on the possibility of creating almost equal or as equal as possible panels on such a mesh, or even analyzing how similar panels are for production, because it's important for production, obviously, to get as many similar panels as possible. Can you say a little bit about that, maybe?
Yeah, sure. I mean, we have these optimizations, the edge length and ideal panel. The ideal panel is, as Matthias said, it's in heavy development. We can analyze the edge length, of course, and these are real numbers, so we can actually have a look at these. These are 3.8 meters, so yeah, these are real numbers. Depending on these numbers, you might want to further subdivide your surface to get a denser pattern, or just to have less subdivision steps in order to make the panels bigger. And in order to make really uniform panels onto a surface, this is, as I said, this is highly dependent on how you start to build up a coarse mesh and what are the requirements for the coarse mesh. For this reference we chose for this webinar, this is, as I said, it's probably not the best reference to show the ideal panel on. But we will have some tutorials in the future for the ideal edge length and ideal panel optimization, and you will be able to see the technology and the results there.
Yeah, well, and maybe a little bit more directly to the question. There's nothing right now in the plugin where you can directly analyze exactly all the panels and see which one are equal or very close. What you can see here is, as Florin has mentioned, the edge length. But we are in a dialogue right now with some partners to find out what exactly the measurements are that are most interesting to industry about the single panels, and there will be definitely possibilities to export much more data about the individual panels in the future. We are trying out some of these tools ourselves in our projects right now, and I'm pretty convinced that in the near future we will have much more output about individual panels of the layouts.
Yeah, Matthias, I would just like to add that we can also be approached if people desire a certain result. We can also do a bit more of the advanced, I would say more than a bit, advanced optimization with our in-house software. As I said before, but this is highly dependent on the geometry too. I mean, this is not magic, this is geometry, and if it can be done on the surface, of course we can be approached to try to do it.
Yeah. Okay, I think we are a little bit over time already. Florin, if you have anything else that you want to get out there, please do so now.
Yeah, I would just like to thank the attendants for watching our debut webinar. We will have more webinars in the future and more tutorials on our website. I hope you're at least like 1/10 of you have the 1/10 of the excitement I have for this product. I really enjoy working with it, and it was great having you today. And yeah, keep an eye on our website, and we will have more exciting things in the future. So thanks a lot for coming.
Yeah, thanks again. Thanks for your interest, and thanks for joining us here. And wherever you are, have a good evening, afternoon, or morning. And looking forward to see you next time. Bye.
Yeah, Matthias, just a short notice. If you have questions, you can also approach us by email. We have the emails listed on our website. Just don't hesitate to shoot an email. And we will, if there are any unanswered questions, we will answer them via email. So yeah. Thanks a lot again.
Thanks. Bye.